Hello and welcome back to Ordinary Differential Equations, the video series where we discuss the concept of a differential equation and how we can use that in applications. And indeed, in today's part 29, we will talk about a result for a system of linear differential equations called Liouville's formula. This one gives us an ODE for the so-called Wronskian determinant and a solution for it. And you will see that this helps us a lot for the system of linear differential equations. However, before I formulate everything, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Steady or Patreon, you can easily download all the additional material with the link in the description. So for example, you can download the PDF versions for the videos themselves, or you can have early access for all new videos. And then without further ado, let's immediately fix our assumptions for this video. So as before, we fix a system of linear ODEs which is homogeneous but not necessarily autonomous. Hence the important ingredient here is the matrix map A of t, which should be a continuous map defined on an interval of R. And now we know by the important Picard-Lindelöf theorem that every initial value problem has a unique solution. Therefore, it's not a problem at all to just pick n solutions, which we call alpha 1, alpha 2, and so on. And since we have an n-dimensional system here, every solution is a curve in Rn. And this also implies that we can easily form a matrix solution where we put these solutions into the columns of a matrix. And as in the last video, we simply call this matrix solution capital U. So it's not complicated at all. A matrix solution is just formed from n solutions of our system of ODEs. And then we already know that we can just define the so-called Wronskian determinant, also called Wronskian. This is quite simple because it's just the determinant of our matrix solution, so there we have a real valued function. And this one we can immediately use to say something important about our solutions. Just assume there is at least one point t0 where this determinant here vanishes. And then by using our linear algebra knowledge, this implies that the columns of the matrix are linearly dependent. But this is only a result for these specific vectors in Rn. So we don't know if the whole functions are linearly dependent, but we definitely know it for these vectors in Rn. And now comes the thing. Linear dependence means that we can find scalars lambda j for the 0 vector in Rn. And indeed this has to be a non-trivial linear combination for the 0 vector, which means not all the scalars can be equal to 0. So the whole equation is quite simple, the sum here is equal to 0. Okay, so this was just linear algebra, but now we can also use that we know that these alpha j's are solutions of our system of linear ODEs. In other words, we can look at the unique solutions of initial value problems. In fact, the 0 function definitely solves a quite simple initial value problem. Namely, the one where the initial value at t0 is just given by 0. But now the thing is that a linear combination of solutions is also a solution of our ODE, but now also the initial value coincides. In other words, this linear combination here on the right hand side also solves the initial value problem. So more concretely, the whole function that sends t to the linear combination is also a solution. Hence the uniqueness part of the famous Picard-Lindelöf theorem gives us that the two functions have to coincide globally. Hence we get that this linear combination here is equal to 0 no matter which t and I we choose. So by definition, this implies that the functions themselves are linearly dependent. So this is a much stronger result because we have the linear dependence in the function space C1. So there you see this is a big advantage of our Wronskian because one point that is equal to 0 is already enough to guarantee the linear dependence in the function space. But obviously we have even more, and this is what we now formulate in the theorem of this video. And obviously the assumptions are exactly the same as before, so we consider the homogeneous part of a linear system of ODEs and n solutions. And then we can simply formulate three properties for our Wronskian determinant W of t. The first one here simply gives us a one-dimensional ODE our w of t has to satisfy. This means we can simply write the derivative of w is equal to the following. Namely, it's a linear ODE where the coefficient in front of w is given by the trace of A. And now if you have never encountered the trace of a matrix, you should just remember it's the sum of the diagonal elements. So it's really not a complicated object, but it comes naturally in here. Indeed, the proof for the claim with the ODE here is not so simple, but it's really straightforward to find the solution of this ODE. So please recall that we have already discussed the general process of solving a linear ODE in one dimension. In fact, it just has to be an exponential function where the starting value is in the front. And of course it works for every initial value problem, so we can just say that we start at t0. And then we just have our ordinary exponential function with the antiderivative of the factor in front in the exponent. Therefore we can just write we have the integral from t0 to t of trace of as ds. And that's it. This is the general solution for the ODE in A. And this formula you can now remember. This is what we call Liouville's formula. So this is something that holds in general for the Wronskian determinant. And now finally the last claim is about our matrix solution U, which could be a fundamental matrix solution. Which simply means that the solutions in the columns here form a basis of the whole solution space. So simply said, this means that the solutions should be linearly independent. And this is satisfied if and only if we find a t0 in I, where the Wronskian determinant w of t0 is not equal to 0. And this claim is quite nice, because we actually have an equivalence here. Okay, then I would say we are ready to start the proof of point A. And for this one, we actually just have to calculate the derivative of a determinant. Indeed, this is the derivative of w that we have in the OND of A. So we just have d dt of the determinant where the alpha solutions are in the columns. And there we can just use the fact that the determinant is linear in each column. And therefore this just results in a product formula in a Leibniz rule where we go with the derivative through all the columns. In fact, this is quite easy to show, and in the end we have a whole sum of determinants. So the second part in the sum just has the derivative here in the second column where the other columns are not touched at all. And this whole thing continues until we have the derivative in the last column. So this is a general nice formula we can use. And then the idea is that we expand each determinant separately. So for example, here in the second part, I want to expand the determinant along the second column. And then obviously here in the last part, we would expand along the last column. However, here the formulation of the matrices with the solutions in the columns makes applying the Laplace expansion a little bit clumsy. Therefore, I first want to simplify the notation in the proof. First of all, we don't need to change the point t at all in the proof, so let's fix that as t. And in addition, let's call the whole matrix we consider here just B. Now this is definitely helpful here, because then we can denote the entries of this matrix by the lowercase letter b. So more precisely, we have b11 in the first corner, then b21 and so on. And in the other direction, we have b12, b13 and so on. And indeed, this makes it much easier to write down our Laplace expansion. And moreover, you might recall from linear algebra that related to the Laplace expansion, we also have the cofactor matrix. So let's call the matrix C, and this one is almost the inverse of the matrix B. So for the definition of this matrix C, you just take the original matrix B, and then you cancel the ith row and the jth column. And then you just calculate the determinant of that times this sign here. And then we get the entry Cij, and with these we form the whole matrix C. And then the really nice property that follows from that definition is that this matrix C is almost the inverse of B. Or more precisely, we should say that the transpose of the cofactor matrix does it. So if we multiply B with this transpose, then we get the identity matrix with a factor. And there it might not surprise you that this factor is exactly the determinant of b. Hence we only have an inverse of b if this determinant does not vanish. Okay, so this is what we want to use here, and if you want to know more about these concepts, you can check out my linear algebra course. In fact, a lot of things we use now come directly from linear algebra. So for example, we will also be interested in the vector given as the derivative of alpha j. And now since we know it's a solution of the ODE, we can also write it as a matrix times a vector. Obviously it's our matrix A of t times alpha j. And now for us it will be easier to look at the entries of this vector, so let's go to the kth component. And then the matrix vector multiplication can be written as a sum. And there let's say that the entries of our matrix A of t are denoted by AKM. And moreover, please don't forget that the entries of our alpha j vector are given by the column in the B matrix. This means the second index is our j and the first index is m. Okay, so now you see that the derivative of our alpha j is just written as a matrix product. And then finally we can put everything together to calculate the derivative of w. And there we already know it's actually given as a sum of determinants. And as you might remember from before, actually every matrix is the matrix B, where one column is substituted by the derivative of alpha j. And there I would suggest that we keep the notation simple. Let's write the matrix like that, and in the jth column we put this. The whole notation is not so important anyway, because now, as you might remember, we want to expand this determinant along the jth column. And this is quite nice, because in this Laplace expansion, we directly get the entries Cij in. This means the Laplace expansion gives us a sum over the entries of this cofactor matrix. Therefore, let's write the sum over the index I, and then we just have Cij times the corresponding entry in the jth column. However, there we already know, this entry is exactly given in this formula there. So we can just copy that, but instead of k, we actually have I. And this is really helpful because now we see that the whole sum over the determinants is just a triple sum over 3 indices. So let's keep it simple. We write the sum over jim and then we reorder the entries there. So first I want to have bmj and then the cofactor matrix C. But obviously by exchanging the two indices here, we can also use the transpose instead of C. This is helpful because then the whole multiplication here at the beginning can be seen as a matrix product. In order to see that, let's put the sum over j inside. So there you should see the matrix product of B with Ct. In fact, what remains there is the entry mi. So to make it clear, we have the matrix product here and then we take the entry mi. And there the good thing is that we really know this entry because it's just given by the entries of the identity matrix. And there you know we have a lot of zeros involved because only on the diagonal we find the ones. Therefore, if we want, we can use the Kronecker delta to describe the entries of our identity matrix, which immediately implies that this double sum here collapses to a single sum. So we just have the sum over the entry I, and the determinant of B is also involved. So in total we just sum up the diagonal of the matrix A and multiply it with the determinant of B. And this is exactly what we wanted because there we have the trace and the determinant of B is our Wronskian determinant. So that's it. This is the proof of part A of the theorem. And now, as already mentioned, for part B we don't have to do much because we just have to solve this one-dimensional linear ODE. Hence, Liouville's formula immediately follows, no matter which starting point t0 we choose from the interval. So with the first two parts shown, we can finally go to the last part, and there I would say in order to prove C, we should refresh our memory what C was about. There we want to show an equivalence between the Wronskian determinant and the fact that we have a fundamental matrix solution. And there you might guess that the fact from the beginning of the video is really helpful for this. And indeed, this nice result we can make even stronger because we actually have equivalences here. So let's quickly check that from bottom to top. So if we have linearly dependent functions, then we definitely are linearly dependent in Rn at every point. So in particular, we also have it at any chosen point t0. And then finally, if we have linearly dependent columns, the determinant has to vanish. And that's it. There we have our equivalence for the Wronskian and the linear dependence. So let's use that and let's write it down in the proof below. And then you see we are almost done with it already. So in fact, the linear dependence means that our U is not a fundamental matrix solution. And now we know by the fact above that this one is equivalent of finding a point where the Wronskian is 0. So it's almost what we want to show, and indeed the missing part comes from Liouville's formula here. Namely, because the exponential function is always positive, it means that if we start at 0, we stay at 0 the whole time. Therefore, this is actually equivalent of having a Wronskian that is 0 everywhere. So this is definitely something you should remember. The sign of the Wronskian is already determined by just one point. Okay, and with that we are basically finished, because we just have to go to the negation of the statements. So the negation on the left gives us that U is a fundamental matrix solution, and the negation on the right says that there exists at least one point where the Wronskian is non-zero. And this is exactly the claim. This is what we wanted to show to find a fundamental matrix solution. But please note, now we also have the similar claim of not having a fundamental matrix solution. And now finally, in total, we can say that the whole theorem about the Wronski determinant is shown. And in addition to that, I can already tell you that Liouville's formula also has a practical value, because one can use it to solve systems of linear ODEs. How this works I will show you in some later videos, and therefore I really hope we meet there again, and have a nice day. Bye bye.